To watch these important lessons, subscribe to DP Education's YouTube channel right now. Click on the bell icon to stay updated on the latest lessons. Sri Lanka's largest free online school, DP Education.
Hi children. Now we are going to start the second chapter of this lesson. Do you remember what we learned in the first chapter, children? We learned about the difference between distance and displacement of a motion, right? So here we are going to learn about force, okay? So what do you know about force, children? Now let's see. We engage in various actions in our day-to-day life. What are the activities that we engage in? So some of them are given below. Write down a list for this one, children. So when you think about this, you can write a lot of activities that you engage in. Right? Write some of them. I will also write some examples. Okay? So what are the activities? So when you go to playground, right? I can write throwing a ball. So at the playground, you do these type of activities. Jumping, running, throwing balls, right? Throwing a ball. So in the classroom, what do you do, children? We can write pushing a desk. Pushing a desk. Right? Then we can write turning pages of a book. Right? Turning the pages of a book. Right? So at home, what are the activities? Sweeping the floor, opening doors, right? We will write opening a cupboard door. Opening a cupboard door. Cupboard door. Then lifting a box or lifting an object. Lifting a box. Likewise, you can write many examples for the things that you do, right? So different, various activities that you do, right? So what do you actually do when you do these activities, children? Have you ever thought about that, children? What do you actually do? So using your arms and legs and sometimes the whole body, you do different activities, right? So throwing a ball. When you throw a ball, how do you throw? You just throw a ball. Pushing, right? It looks like you're pushing something, right? So pushing a desk, also pushing, right? Turning the pages of a book. How do you turn pages? You take the page, carefully you turn it. So here, pulling. You are moving up, pulling. Okay? Opening a cupboard door. So when you open a cupboard door, you have to pull the door towards you. When you close it, you have to push it away from you. Pulling, pushing. Right, children? Right. So, lifting a box. So when you lift a box on the ground, lifting up, pulling towards yourself. Right? This motion is pulling from up, down to up. Okay? So I gave you only 5 examples. All these examples, when we think about what actually happens, either pushing or pulling takes place. Right? Is it the same with the list that you wrote, children? Just check whether it's the same, whether any kind of pulling or pushing is there. So when we actually think about the activities, physical activities that we do, you will realize always a pushing or a pulling is engaged. Right, children? Okay. So what do we do during these actions? You may have understood that a pull or a push is applied during all these actions. If you go through your list carefully, you will figure out, right? Either pulling or pushing is applied, or sometimes both are applied in all these activities, right? There are instances that both the pulling and pushing are applied, okay? So here, pulling a table. You all can see he's pulling towards himself. Riding a bicycle. How do you ride a bicycle? You have to push this pedal, right? So here you have to give a push towards. When you go forward, you have to give a push to the pedal and then it rotates, making the bicycle move. You have to push it with your feet, right? Push in a table. You have to push it away from you. So all these three instances, push in, pull in, applied. Right here, pull in. Ride in a bicycle. We will write it separately, right? So here, pull in is applied. It's a pull. This one is a push. This is also a push. Right, children? So lifting a bag is an upward pulling. Right? Lifting a bag, upward pulling. Right? When drawing water from a well, a pull is applied. Drawing water from a well, how do you draw water? Right? So here we will draw a diagram for that one. So if you consider lifting a bag, okay? So if this is the bag, when you pull it up, right? When you pull it up, what happens? It's always an upward pulling, right? You pull it upwards, lifting a bag, and upward pulling. So when drawing water from a well, a pull is applied. Drawing water from a well, let's say that this is a pulley. In some wells, the pulleys are fixed. Let's say using pulleys that you draw water. So if this is the bucket, water bucket, right? If this is the water bucket, and you always pull it towards your side, okay? That rope goes around this circular pulley. This is known as the pulley. You must have seen in some wells, these type of pulleys are fixed, right? Circular metal structure is fixed and the rope goes around this pulley. Okay, this is a type of a simple machine, right, children? So here, when you draw water from a well, you can use something like this, right? You always have to pull it downwards, pull it downwards. Here pulling upwards, here pulling downwards. Okay, children? So lifting a bag is an upward pulling. When drawing water from a well, a pull is applied, right? So when riding, let's say that if we are going to draw water without this type of things, we just have to draw water by using an upward pulling. If you use something like this, a pulley like this, it is a downward pulling. Okay? So when riding a bicycle, the push is applied. Here we discussed about it, by the feet on the pedal. Right, children? So after going through all these things, it's very clear that when we do all these activities, just any activity, either a push or a pull is applied. Okay, children? Right. So here we have to do this activity to understand this better. Activity. Finding out more about pulls and pushes. Right? Engage in the following activities. Mention whether the action done is a pull or a push. So you all have to do this now by yourselves. And after doing that, you have to watch this video. Okay? Right. So we will go through this list given. Action done, you have to mention whether it is a pull or a push. First two are done. Okay? Pushing a table, drawing water from a well, lifting a bag, riding a bicycle, turning a tap, hitting a ball, writing with a pen, brushing teeth with a toothbrush, erasing pencil lines drawn in a book, applying brakes of a bicycle. Okay? So here pushing a table, it's definitely a push. Drawing water from a well, we just discussed that it is a pull, upward or downward, however we have to pull, right? Drawing water from a well is a pull. Lifting a bag, it again is a pull, right? This is also a pull. riding a bicycle. So when you ride a bicycle, you have to push the pedal using your feet. Okay, therefore it is a push. Right, children? Turning a tap. So when you turn a tap, let's say that using these two fingers, when you turn a tap, what actually happens? Now in the upper grades, you are going to learn there are something called couple forces. So turning a tap is such couple force. Okay. So here turning a tap. Let's say if this is the tap, when you turn it from one side, from here you pull, from here you push. Pushing and pulling both involved. Therefore, turning a tap is a type of a couple force. It's a push and a pull. Push and pull. Push and pull. Right? Hitting a ball, hitting a ball, or throwing a ball, hitting a ball. They all are pushes, right? Push. Next one. Writing with a pen. So when you write with a pen, think what you have to do. Sometimes you have to push, sometimes you have to pull. When you write letters, sometimes you move the pen away from you, it is a push. Sometimes you have to move the pen towards you, it is a pull. Right? Push and pull. Brushing teeth with a toothbrush. Brushing. Right? Push, pull. Push, pull. Likewise, okay? Push and pull. Erasing pencil lines drawn in a book. Erasing again, you have to erase. Push and a pull both, right? Push and pull. Right? The last one, applying brakes of a bicycle. So if you ride bicycles, you all are very familiar with this one. How do you apply brakes on a bicycle, children? So if you consider the bicycle handle, it's something like this. Let's consider if this is the bicycle handle, right? This is the axis, whether it's connected to the other part of the bicycle. Right, you all know that from another place, the brake is connected like this. So when you want to stop the bicycle, what do you have to do? So here, from here only you are holding the bicycle. This is the handle. And if you want to stop the bicycle, you have to simply pull these two levers towards you. Right, therefore it is a pull. Okay, it is a pull. Right, applying brakes of a bicycle, it is also a pull. Okay, pushing a table, it is a push. Drawing water from a well is a pull. Lifting a bag also a pull. Riding a bicycle is a push because you have to push the pedal forwards. And turning a tap, push and pull both. And hitting a ball is a push. Writing with the pen, push and pull. Brushing teeth, push and pull. Erasing pencil lines again, push and pull. And applying brakes of a bicycle, you have to pull. Right, children? So you can write a longer list and try to understand this better. Check whether it is a pull or a push or both of them. Right, children? So you will understand at least one of these push or a pull or one of these is done in all the activities that we do. Right, children? So we'll move on to the next. Right. So here, every time when we do work, right, any activity, we either push or a pull. Right? So to do any physical activity, you all know you have to apply force. Without applying force, you cannot do the physical activities. Okay, children? So here at the same time we learn that in order to do these activities, you need to either push or a pull, right? Push or pull things. Okay, children, which means now we can come to a conclusion. A force means a push or a pull. Okay, pulling or pushing is known as applying a force. If you want to apply force onto an object, you need to either push or pull it. Okay, children, so this is very important. This is very important. Pulling or pushing is known as applying force. Okay, children, pulling or pushing is known as applying force. Look at this pulling movement. Now, this is also pulling. Here, this person is pulling a car towards him. Right? This child is pushing this cart. Okay, pushing this cart. So this is the pulling, this is the pushing. Right? When pulling a car, the rope attached is pulled and a force is applied on the car. So the rope is attached to the car. The person is pulling from these ropes. Therefore, in order to apply force on the car, ropes are used. So when the pulling force is applied on the ropes, as the ropes are attached to the car, automatically that force is applied on the car as well. Right? When pulling a car, the rope attached is pulled and the force is applied on the car. Right? So what is done by the child when pushing the trolley is the forward application of a force. Forward application of a force. Okay? So a large force should be applied to push a heavier table than to push a lighter one. In order to move or in order to get a bigger work done, we need to apply more force. Okay, so to understand this better, we are going to do a simple activity in the lab, right? So the activity is finding out about the amount of force applied on an object. We are going to understand whether we need to apply more force or less force. When the work done is different, the force applied is also different. This is what we are going to prove by this activity. Okay, so finding out about the amount of force applied on an object. Right, children? So in order to do this activity, we need two similar wooden blocks and a rubber band and a balance like this. This is called a Newton spring balance. I will show that in the lab. Okay, let's write down. Right. Two similar wooden blocks. You need two similar wooden blocks, a rubber band, and a Newton spring balance. A Newton spring balance. A Newton spring balance. Right, children? Two similar wooden blocks, a rubber band and a Newton spring balance. Okay? What is the method? Place a wooden block on a table and pull it using a rubber band attached. So using a hook, you have to attach a rubber band to the wooden block and then you have to try pulling it. Okay, so how to do this activity? We'll draw a small diagram to show this. Right. Okay. So if this is the wooden block, we can simply fix a hook to this one and then you have to attach a rubber band. Using the rubber band, you have to pull it. Right? You have to pull it. Right, children? Next one. place the other wooden block on the first block and pull again using the same rubber band. Okay, so this is the first instance. In the second instance, what do you have to do? Do the same, but this time with 2 wooden blocks. Here we are going to use 2 similar wooden blocks. Okay, here. So you need to use 2 wooden blocks this time. And you have to place one over the other. Right, children? And then again, now this should be the one with the hook. The bottom one should be the one with the hook. And then using the same rubber band, you have to pull these 2 again. Right? You have to pull these 2 again. Right, children? Okay. Right? Number 3. When the motion starts, the rubber band will stretch longer. Okay, so you will realize, we will draw it separately. Okay. We will draw a longer one. So you will realize this one stretch. The rubber band stretches longer. Okay. So when the motion starts, the rubber band will stretch longer. That means the force applied later is larger. The first instance with only 1 wooden block, you have to check how long the rubber band stretches. Second instance with 2 wooden blocks, you will realize the rubber band stretches longer. Okay, which means more force is applied, because pulling or pushing means applying force. Okay, so if in order to pull this one, if the rubber band stretches more, which means more force is applied. Okay, so next one. Repeat the activity using a Newton spring balance instead of the rubber band. So when we consider the Newton spring balance, I will show you all. So this Newton spring balance has a metal spring inside it. It stretches. So instead of the rubber band, we have to follow the same steps we followed here. This time using the Newton spring balance. Right? So the first step, we pulled 1 wooden block using the rubber band. Right? So as the third step, what we have to do is, instead of this rubber band, we have to fix the Newton spring balance. And we have to pull it. So using the Newton spring balance, we can measure the force applied. Okay, so Newton spring balance is the instrument that we can use to measure the force applied on an object. Right? Here when you use the 2 rubber bands, the same rubber band in 2 instances, you will realize in the second instance it stretches more, which means more force is applied. Right? The next steps, you have to do the same 2 steps. You have to follow the same 2 steps. Instead of the rubber band, you have to pull it using a Newton spring balance, and the way it stretches will be different, and the value given by the Newton spring balance in each instance will be different. So in the second instance, higher value will be given by the Newton spring balance. So that is what we are going to observe in this activity, right? So repeat the activity using a Newton spring balance instead of the rubber band, right? Record the readings of the Newton's balance on both occasions. The amount of force applied can be obtained numerically, in numbers. Okay, when you use the rubber band, you cannot obtain the value. Okay, the amount of force applied cannot be observed numerically. Right? You can just see that the second instance, the rubber band stretches more. But when you use the Newton spring balance, as a number, you can measure it. So let's do this activity in the lab. Right, children? So we are going to do this activity to understand about the force that is applied on an object. Okay? So as I explained you all before, here I have 2 wooden blocks. We have fixed one hook in 1 wooden block. Okay? And I have a rubber band here. and a Newton spring balance. This Newton spring balance is used to measure force. Okay, right. So first of all, I'm going to pull this wooden block using the rubber band. Okay, check how much this rubber band stretches when I'm going to pull this wooden block using this. Okay, right. Okay, so this amount is stretched. So without stretching, without pulling this one, this is how the rubber band presents. Now when I pull it, this much is stretched. Okay, children? Right. So now I am going to place this other wooden block on the first wooden block, and then both the wooden blocks I am going to pull using this rubber band. Now check, children, it stretches more this time. Right, children? It stretches more. Earlier, without the second wooden block, it stretches only a little distance. Now, the length is higher. Okay, children? Right. So, why does this happen, children? Now, in the second instance, rubber band stretches more, which means more force is applied here, right? Because the force applied by the rubber band is higher, it stretches more. So, what is the force applied? Now, as I explained you all before, force can be measured using this Newton spring balance. Right. Let's see this one now. This time I'm going to pull this wooden block using the Newton spring balance. Observe carefully. This is the Newton spring balance. Here you all can see a spring. When I stretch this one, you all can see the length of the spring increases, and thereby here this area is calibrated. So you all can see this disc-like part on the top is the indicator. So when I stretch it like this, now here it is at, now this side is Newton, capital N. Now it is at 0.5. It's at 1. Now this time it's at about 2.5. So that's how you take the reading. Okay, this time when I pull it like that, the force applied is 2.5 newtons. Okay, right. Now I'm going to measure the force applied on this wooden block when we pull it. Now here I'm going to do this with the spring balance. Okay, so observe very carefully how it happens. Observe where this disc-like indicator moves. Okay, when it is moving, the wooden block is moving. Right. Now here you all can see it is somewhere around 0.5 to 1 Newton. Now this wooden block is moving, which means the force applied is between 0.5 to 1. We can take it as 0.75. Okay, observe carefully again. See, now the wooden block is moving. If I don't pull it, this indicator moves up, wooden block also stopped. Which means in order to move it, I have to pull it more. Right, now it is moving. So it is somewhere around 0.75 newtons. So the force applied can be taken as 0.75 newtons. Okay, now I'm going to measure the force applied when we move both the blocks. So I'm going to place this block on the first block, and now I'm going to again pull these two blocks using the Newton spring balance. So observe what the amount is. Here what, children, you all can see the indicator this time is between 1 to 1.5, 1 and 1.5 newtons. We can take it as 1.25 newtons, right? About 1.25 newtons. So observe it again. So here the indicators in between 1 and 1.5 newtons. So we'll take it as 1.25 newtons. Okay, children? Right. So earlier the force applied when only one block was there, the force applied was about 0.75 newtons. Now this time when we use both the blocks, the force applied was, what happened, children? It increases. It's about 1.25 newtons. Right? So when we add two blocks, what happens to the mass of the entire unit or the object? The mass increases. So you can come to a conclusion that when the mass increases, the force applied to move these two objects or the entire setup is also increased. Right, children? So you all observe what happened here. So in the first instance, we tried to pull one wooden block with rubber band. So you could see the rubber band stretches when we pull, right? In the second instance, we used two wooden blocks, okay? So we kept one wooden block over the other, and this time when we pull, you could clearly see that in the second instance, the rubber band stretches more, which means this happens because more force is applied to pull two blocks. Why does this happen? Because the two blocks means now one box, the mass of one box is less than that of the mass of two boxes, right? So here in the third instance, what we did was we did the same activity using a Newton spring balance. Now you all know using the Newton spring balance, we can measure force in newtons, right? So here you all observe when we use only one wooden block, less amount of force is applied, but when we use two wooden blocks, what happens, children? More force was applied. The reading was higher. Reading of the Newton spring balance was higher in the second instance. Right, children? So this happens when the mass increases. What happens, children? The force applied also should be increases. Okay? We will write down this observation. Okay? We will write it separately. Two instances with the rubber bands and the Newton spring balance, right? The rubber band, when the rubber band stretches more, when two wooden blocks are pulled. Right, in the second instance, the reading of the Newton spring balance is higher when two wooden blocks are pulled. Right, children? The rubber band stretches more when two wooden blocks are pulled. The reading of the Newton spring balance is higher when two wooden blocks are pulled. So what is the conclusion? When two wooden blocks are pulled, more force is applied. Right? We will write that. When two wooden blocks are pulled, more force is applied. So we'll write within brackets, when the mass increases, now two wooden blocks means higher mass, right? When the mass increases, the force applied, mass increases, the force applied also increases. Or the force applied to pull the blocks increases with the mass. Okay. So when 2 wooden blocks are pulled, more force is applied. When the mass increases, the force applied also increases. Okay, children? Right. The rubber band is stretched less when there is 1 wooden block, and it is stretched more when there are 2 wooden blocks. Okay? That means more force is applied on the second occasion. So when you compare the readings in the spring balance, it can be understood properly. So using the Newton spring balance, you can get the reading, like numerically you can understand this. Okay? So right, children, so as I explained you all, Newton spring balance is used to measure the force, right? So we can use, as the unit, we can use Newton, okay? The international unit of measuring force is Newton. Newton. So what is the symbol? Capital N, right? The equipment used to measure force is Newton spring balance. So you also saw it during the activity. Right, children? This is the Newton spring balance. Right, children? We'll move on to the next. Right. We have this other activity to do. Take a balance calibrated in grams or kilograms and a spring balance calibrated in Newton. So here I'm going to use a Newton spring balance. It is calibrated in both the units. Right, one side is calibrated in newtons, the other side is calibrated in grams, okay? So weigh the same object using both balances and record the readings in a table as given below. Here you don't need to measure the weight twice, right? Now I will explain you all. Weight is measured in newtons. This mass and weight are the same things, children. After this we will understand that, right? So here weigh the same object using both balances. So here we are using one Newton spring balance with both the scales. Therefore, we don't need to weigh them twice. Okay. So record the readings in a table given below. Develop a relationship between weight and mass with the help of your teacher. So now we think weight and mass are the same things. So after this activity, we are going to realize they are not the same. They are two different things. Okay, children? We'll do this activity in the lab. Right, children. We are going to do this activity to make a relationship between weight and mass. Okay? So here I have a Newton spring balance. Observe this very carefully, children. Even earlier we used this type of spring balance. In this side, it is calibrated in newtons. So this side is calibrated in newtons. Newtons is the unit that we use to measure force. Okay? Look at this side. This is calibrated in grams. Okay, children? So you all can see from 100 grams to 1 kilogram is calibrated, mentioned here. Okay? So which means when we use this Newton spring balance, not only the force but the mass also can be measured using the same balance, right? So grams, kilograms, milligrams we use to measure mass, right? Gram is a unit used to measure mass. So from this side, using these numbers, you can measure the mass. Using this side, as it's calibrated in newtons, you can measure the force. So using these values, when we measure each of these objects using the values we get, we are going to build up a relationship between mass and weight. Okay, now weight is a type of force. Okay, weight is a type of force. Therefore, weight is also measured in newtons. Okay, children? Right. Okay, first of all, I am going to measure this. Now here I have a wooden block, a small rock, and here I have two weights of different sizes. Okay? Right. First of all, I am going to measure the wooden block. Okay? Right. Right. So if you observe carefully, children, so when you take from the gram side, you all can see it is 600 grams. right? Indicators at 600 grams. In the Newton side, it is at 6, which means 6 newtons. So here, so the mass, so what? Using grams, we measure the mass. Therefore, the mass of this wooden block is 600 grams. And what is the force applied here, which means the weight? Weight is 6 newtons, okay? Right. Now I will take the second object, the small rock. So here I am going to hang it like this and observe this time also carefully. Observe carefully, children. So if you observe carefully from this gram side, or which means the mass of the rock is 200 grams, right? So what is the value given in the Newton side, right? That is 2, okay, which means the mass of this rock is 200 grams and the weight of the object is 2 newtons, okay, right. Okay, now I'm going to measure the third object, right. Okay, observe carefully, children. So what is the mass of this object, children? What is the mass of the object? Mass is, you all can see, about 150 grams. It's between 100 and 200. Therefore, we can take it as about 150 grams. So what about the weight, children? When you consider the Newton side, the weight side, it is about 1.5 newtons. Okay, it's between 1 and 2. Therefore, we can take it as 1.5 newtons. Okay, right. And I will take our last object, the other bigger weight, right. Observe carefully, children. You will see if you take the mass measured or calibrated in grams, it's about 300. It's almost 300 grams. Okay. So what is the weight? The weight is given in newtons, right? So when you consider the weight side, it is 3 newtons. It's at 3. Okay. Right? Right. Right, children. Now we measured the masses and weights of all these objects, and now we are going back to the class to make the relationship between the mass and weight. Right, children. So you all observed what happened. So we will write our readings here. So object weight, mass and weight. Okay. So I'm going to complete this table. So we weighed 4 different types of objects. We will write them first here. Right. Right, children. So let's write objects weighted. What did we use the first object? Wooden block. Wooden block. And then a rock. Large weight. Small weight. Small weight. Okay. So what was the mass of the wooden block, children? It was 600 grams. But you have to mention it here in kilograms. So how to convert grams to kilograms? You have to divide it by 1000. Okay. So you can cut these two zeros to these two zeros. What is the value? 6 divided by 10, 0.6. 0.6 kilograms. So the second one, mass of the rock was 200 grams. So how to convert it to kilograms? 200 divided by 1000. Then you will get 0.2 kilograms. So the third object was large weight. What was the mass of it? It was 300 grams. So convert it into kilograms. 300 divided by 1000 equals, these two zeros to these two zeros you can cut. 3 divided by 10, 0.3. Right, children? What was the mass of the small weight? It was 150 grams. So we'll convert it into kilograms by dividing it by 1000. So the answer is 0.15. 0.15. Right, children? So the masses of them after, now we measured them in grams, but here you have to mention in kilograms. Right, wooden block 0.6 kilograms, rock 0.2 kilograms, large weight 0.3 kilograms and small weight 0.15 kilograms. Right, children? So what was the weight? Now there I showed you all, we measure the weight in newtons. Okay, we measure the weight in newtons. Here it was 6 newtons. Right, children? Here it was 2 newtons. Now when I write down this one, you can see there's a kind of relationship between these two things. Okay, this is 0.6, this is 6. 0.2, 2. Right, this one 0.3. What was the value in newtons when we measured? It was 3 newtons. And the small rock, weight of the small rock was 1.5 newtons. Right, children? So after going through this one, now here you have to record the readings in a table and develop a relationship between weight and mass with the help of your teacher. Now this concept you are going to learn in the upper grades, children. Right, we are going to briefly learn about this here. Okay, so here we will take the first object, wooden block. Mass is 0.6, weight is 6. So if you multiply the 0.6 by 10, what will you get? It is 6. Here 0.2. If you multiply 0.2 by 10, it will become 2. These two also the same. If you multiply 0.3 by 10, we will get 3. If you multiply 0.15 by 10, you will get 1.5. Which means we can simply write down it as, right? We will simply write down this. I will divide it here. We can write a small relationship here. Okay, we can write weight equals mass into 10. Weight equals mass into 10. Right? Look at this one. Weight equals mass into 10. So when you do your calculations in this lesson, you can use this one. But actually, what is this 10, children? This 10 means the gravity, or we can say gravitational acceleration, very simply gravity of Earth. Right, children? Gravitational acceleration on Earth. Now we all know when you consider the Earth and all the other planets, there is a type of force called gravity. Because of this gravity, let's say that if we throw something up, it will always come down. If we jump up, we will always come down. What is the reason, children? This is because something is thrown up is again attracted towards the ground by the gravitational force or gravity. Right? This gravitational force changes from one planet to the other planet, children. Okay? So we consider the gravitational force. This actually we call it gravitational acceleration. You are going to learn this in the upper grades. Okay? The gravitational acceleration of the Earth is 9.8. This 9.8 round off value is taken as 10. Right? This is actually the gravitational acceleration on Earth. So, we will write another relationship here. Right? So, weight equals mass multiplied by gravitational acceleration. Gravitational acceleration. Right, children? So we can simply write the relationship like this. So when the object is on the Earth, this gravitational acceleration is 10. Right, children? So in different planets, this value is different. What about the mass, children? Mass will be the same. Now in grade 6 we learned the definition of mass. What is the meaning of mass? Mass means the amount of matter. Now when we consider matter, matter can be three ways: solids, liquids and gases. Right? So when we consider a certain object, the amount of matter present in a certain object is known as its mass. Right? So let's say that if we take a particular object to a different planet, the amount of matter present in that object will be the same. It's not going to change. But the gravitational acceleration depends on the location. Right? This is the amount of force applied by the Earth or the ground. So if we take it to a different planet, the amount of force, right, downward force applied by that particular place, particular planet on the object is different. Right? So this value changes from planet to planet, but this value is not going to change. It's just one object. The amount of matter present in that object is going to remain the same wherever the object is. Right, children? So weight equals mass into gravitational acceleration. So on the Earth, it is 10. It is actually 9.8, but we consider it as 10 when we do the calculations. Right, children? So our day-to-day life now we say, my weight is 45 kilograms, right? My weight is 30 kilograms. You have to measure 1 kilograms of sugar. But in science, now we know this weight and mass are two different things. What is given in grams, kilograms, milligrams, that is actually not weight, that is mass. Weight is given in newtons. Right? Weight is measured in newtons. Just in our day-to-day lives, right? We use this weight in the normal way, like in kilograms, grams. But remember, in science, this is different, children. Right? Mass is not weight, weight is not mass. They are totally two different things. So when gravitational force acts on a certain object, mass of a certain object, we get a certain value, and that value is known as weight. Right? So even though in day-to-day life we express our weight is 40 kilograms, 1 kilogram of sugar, now you know that here it's different. Okay, actually weight is expressed in newtons, right? In kilograms, grams, milligrams, mass is expressed. Right, children? Okay, so weight and mass are not the same things. Right, we'll move on to the next. Right, so we have another activity to do, showing that force has a magnitude and a direction. Now, do you remember in the first chapter we learned about distance and displacement, right? We learned that distance has a magnitude. Now, what is magnitude? Magnitude means the size or the amount. Distance has the amount, as an amount, but distance does not have a definite direction. But displacement has both magnitude and a definite direction. Right, children? So we gave a name to quantities with a definite direction and a magnitude. What was that name? Vector quantities. Right? So in this activity, we are going to show that force is also a vector quantity. Right? We are going to show that force has a magnitude and a direction. Okay? So what do we need? We need a Newton spring balance, a piece of thread, and a wooden block. Okay? Let's write. A Newton spring balance, a piece of thread, and a wooden block. Okay, we need a Newton spring balance. Right, a Newton spring balance, a piece of thread, and a wooden block. Okay, so it's very easy to do this activity. We will label this diagram first. Wooden block, thread, and Newton spring balance. Wooden block, thread, and Newton spring balance. Newton spring balance. Right, children? So how to do this activity? Attach a Newton spring balance using a piece of thread to a wooden block kept on a polished table, like this. Pull the block using the Newton spring balance, right? Attach a thread to the wooden block, then attach the Newton spring balance to the other end of the thread, and you have to pull it, right? Observe the direction of the motion of the wooden block. So when you pull this one using the Newton spring balance, you have to check to which direction this wooden block moves, and the direction of pulling the thread. In the same way, you have to check to which direction the thread is stretched. Okay? Push the wooden block while it is on the table. You have to push it. Now you have to remove this spring balance, and then you have to push it from one side. Push the wooden block while it is on the table. The direction of pushing is the direction of applying the force. Check whether both the directions are the same, right? Observe the direction of pushing the wooden block and the direction of the motion of it. Right, children? We'll do this activity now. Right, children? By this activity, we are going to check whether force has a direction. Now we know that force has a size or a magnitude, okay? So using the Newton spring balance, we can measure the size of the force, Okay, in Newton. Okay, children, this force has a direction too. Let's check. So here I have a wooden block. I need to move this wooden block along this surface, right? So how to move this wooden block? Now I can pull from this side or I can push from this side. If I want to move this wooden block from this place to this place along the surface, there are two ways to do that, right? I can pull this wooden block from using this hook or I can push it from this side. Okay, children? So first of all, I am going to pull this wooden block using this Newton spring balance. In that way, we can measure the force applied in order to pull this wooden block. Okay? Right. So now you all are familiar with the Newton spring balances like this. Okay? Right. So observe carefully. Look at the Newton side. Now this is gram side, or the mass side is also there. You have to look at the Newton side in order to find out what is the force applied when we move this wooden block. Okay? Right. So observe, you can see it's about 1 Newton. Right. So when I move this, it is about 1 Newton, which means the size of the force applied here is 1 Newtons. So is there a direction? So when I move this one, right, when I pull this wooden block from this direction, you all can see this wooden block moves to this side. Look at the side of this direction of this thread. Thread is also directed towards this side. Okay. So the thread is also directed toward this side. Wooden block also moves towards this side. Okay. Right. So what will happen? Now that is when we are pulling this object, right? But if I push this object, if I want to move this wooden block into this side, I have to apply force from this direction towards the same direction that we want to move the wooden block to. Right? What will happen if I want to move the wooden block to this direction, but I'm applying force from this direction? It does not move to this direction. Instead, it is moving to the direction that I'm applying force to. Right, children? Which means force has a definite direction too. Right? If I'm moving this wooden block to this direction, what is the direction of force? I am applying force towards this direction, the same direction that I want to move this wooden block. And at the same time, if I want to move the wooden block to this direction, then I need to apply the force from this side towards the same direction. If I apply from a different direction, it won't work. Right? So after doing this activity, it's very clear that force has not only a size or a magnitude, but it has a definite direction too. Right, children? So it was very clear when we were doing the activity, when we were pulling the object, pulling the wooden block, what happened? The wooden block moves towards the same direction of the pulling of the thread, right? To the same direction. When the thread pulled to one direction, to the same direction, wooden block also moves. So when we push the wooden block, what happens? The wooden block moves towards the same direction of pushing, which means after doing this activity, it's very clear. And at the same time, we could measure the size or the magnitude of the force using the spring balance. Right? So it's very clear that there is a magnitude. Okay, and at the same time, because the direction acted also in the same way the force is applied, it's very clear that force has a direction too. Okay, let's write these things. Okay, when pushing, when pulling, the wooden block moves to the same direction of pulling the thread. When pushing, wooden block moves. To the direction of force is applied. Pushing force. Force is applied. One more thing we can write. We can measure the magnitude of the force with the Newton spring balance. Right? When pulling, the wooden block moves to the same direction of pulling the thread. Right? When pushing, the wooden block moves to the direction of force is applied, and we can measure the magnitude or the size of the force with the Newton spring balance, right? Okay, so what is the conclusion? So it's very clear that force has both magnitude and direction. Okay. Force has both magnitude and a direction. Which means it is a vector quantity. Vector quantity. Okay? Force has both magnitude and a direction. So, under the lesson, now we know two quantities as vector quantities, displacement and force. Okay, children? We'll move on to the next. Right. So, this is our last topic of the lesson, effects of force. Effects of force. Under this one, we are going to learn what are the things that we can do by applying force. Okay? So, here we will go through this. So, this is number 1. An object can be moved by applying a force. Let's say that if a certain object is at rest, we can move it by applying force. Okay, let's say if there's a ball, we can move it by applying force, pushing it or pulling it. Okay, at the same time, moving objects can be stopped by applying a force. Okay, so let's say that if someone is throwing a ball at you, when you catch it, its movement stops. When you catch, you apply force. Okay, so by applying force, you can stop a moving object too. Right, look at these examples. An arrow at rest means not moving. An arrow at rest can be moved by applying force to a bow. You have to stretch the bow and then you have to release it. Then the arrow will start to move. Okay. A vehicle at rest can be moved by apply a force by its engine. Okay. When you start the engine, vehicle will start to move. Okay. A ball at rest can be moved by hitting it with a bat. Right. Or kicking it. Okay, children. This living as well as non-living object at rest can be moved by applying a force. Right, children? So, it's very clear as the first effect of force, an object can be moved by applying a force, and at the same time, the moving object also can be stopped by applying a force. We can even take them as two different points, two different effects. Okay? Right. Look at this second one. The speed of an object can be changed by applying a force. Speed can be changed by applying a force. Just imagine if someone is pedaling a bicycle, if you go from behind and pushing the bicycle forward, what will happen to the speed? The speed will increase. And at the same time, let's say when small children ride their bicycle, if you go from the front of the bicycle and if you hold it, what will happen to the speed of the bicycle? It will decrease. Right? Which means we can, by applying force, pushing or pulling, we can change the speed of a moving object. Right? So look at these examples. The speed of motion of a bicycle can be increased by increase the force applied to its pedal. Right? Or the rider can increase the pedaling speed and we can increase the speed. The speed of it can be decreased by applying brakes. When you apply brakes, what happens? Earlier also we learned this. The speed of the bicycle can be reduced. Right? An animal can change its speeds of moving by changing the force applied to its limbs. Right? When you are in a hurry, by applying force to your legs, you can move fast, walk fast. Right? And at the same time, when you run fast, when you are tired, what do? By applying force to your legs again, you slow down. Okay? Right. The speed of a vehicle can be increased by treading on an accelerator and it can be decreased by applying brakes. Using accelerator of the vehicle, we can increase the speed. Using the brakes of vehicles, we can decrease the speed. Right? So the second effect of force is the speed of an object can be changed by applying a force. Okay? Right. Number 3. The direction of motion can be changed by applying a force. Right? Let's say that, look at the first example. Right? A cricketer can, right, or a batsman can change the direction of ball coming towards him using the bat. Okay, here this is tug of war. Right? When this group of people pulling the rope to this side, this group of people by applying force, they pull the rope to their side. Right? The direction, when this one is moving, when this rope is moving towards them, by applying a higher force, they can move it to this direction. Right, children? So here, same thing happens here also. Right? Two dogs are fighting for the same thing. Right? A cricketer can change the direction of the ball by hitting it. Ball is coming towards him. When he bats, what happens? Using the bat, he can hit the ball and send it to a different direction. Right? In tug of war, each team tries to change the direction of motion of the rope by applying force. Two puppies are applying force to drag the bone towards itself. Okay, just like this tug of war. Right, children? So the third effect of force is the direction of motion can be changed by applying force. Right? Number 4. Rotation or a turning effect can be resulted by applying a force. Even earlier we discussed about turning a tap. Right? When you apply force onto the tap, what happens? It starts rotating. In the same way, if you apply force onto the steering wheel, what happens? It starts rotating. Right? Look at this bicycle handle. You can move the handle by applying force. You can it's a kind of rotational movement. Okay, when a force is applied to a tap, it turns. Right? The steering wheels also turn when a force is applied. How do you turn a bicycle when you are riding? Right? How do you turn a bicycle? It's done by applying a force on the bicycle. Right, children? So here, as the fourth effect, we can learn rotation or a turning effect can be resulted by applying a force. Right, children? Next one. The shape of an object can be changed by applying a force. Right, children? This is number 5. Right. So look at these bending bars. Okay. So here it's a clay ball. Okay, it's a plastic ball. By applying force, you can change its shape. In the same way, when you make different things, when you mold different things with clay or Play-Doh, again by applying force with your fingers, you can make different shapes. Shape is changed, right? Bending iron bars are done in various displays. Then the shape of the iron bar changes, okay, when you bend it. Various goods are shaped with clay by applying force, okay? The shape of plastic goods can be temporarily changed by pressing them. Right, children? So changing the shape due to the force applied to it occurs in such occasions. Right, children? So number 5, the fifth effect of force is the shape of an object can be changed by applying force. Right. So now we know that by applying force, we can do different things, right? We can move an object at rest by applying force, and at the same time, we can stop a moving object too, right? We can change the speed of the motion, speed of a moving object by applying force. Okay, children? And at the same time, rotational effect also takes place sometimes because of applying force. Okay, children? Sometimes by applying force, we can change the direction of a moving object. And here we learn by applying force, we can change the shape of objects too. Right, children? So I hope you understood the effects of force clearly. Right? Okay, we'll move on to the next. We have this assignment to do. This is a very easy assignment. You all can do this, right? Recall instances of applying forces by you today. There are so many instances that you must have used. You must have applied force, okay? So prepare a list of uses that you get by applying those forces. I will show you how to do this activity, right? So we can simply do it in a table, right? Like this. You can make the list longer and you will understand it better when you do more examples, right? So here instances of applying force, instance. And then you have to write, prepare a list of uses that you get, uses. Right? So instances of applying force. You can do it in two ways, children. Sometimes you can take it as pushing or pulling separately and what are the uses, each instance you used. Or you can straight away use it as separate instances, like I'm going to do now, right? Brushing teeth. Brushing teeth, you have to apply push and pull both, okay? Brushing teeth. So when you brush teeth, what is the use? Your teeth becomes clean, okay? That is the use. Teeth becomes clean. Teeth become clean. Right? So, another one. Opening a tap. Right? Opening a tap. When you open tap, you will get waters, right? So you can clean things up, okay? Obtaining water. Obtaining water to clean, right? That is the use. Likewise, this is a very easy activity, children. You all must try this, right? I will do one more example. We can write writing with a pen. So uses, when studying you need this, right? Study or study. You can write either way. So you can make a list like this. Recall instances of applying forces by you today. Prepare a list of uses that you get by applying those forces. So when you do these things, it's better. Within brackets, you can write whether it's a push or a pull too. Right? Brushing teeth, push and pull both. Opening a tab, push and pull both. Right? Writing with a pen, again push and pull both. So when you make your list longer, you will get more examples, right? You will understand it better. Right, children? We'll move on to the next. So here under extra knowledge, we are going to still read this. We will go through this. A force is exerted by the center of the earth on all the objects on the earth. What is the name? Now I explain you all. This force is known as gravitational force. Right? We briefly discussed about this. The weight of an object is the gravitational force exerted on the mass of the object. Even this one I briefly explained. Right? The weight means the gravitational. When the gravitational force acts on a certain mass, that is known as weight. Right? Though the mass of an object is always constant, which means the mass does not change. Mass means the amount of matter present in a certain object, right? Though the mass of an object is always constant, its weight may slightly change from place to place because of the change of gravitational force, right? From planet to planet, place to place. The gravitational force of the moon is about 1/6 of that of the earth. It's a fact, right? Therefore, the weight of an object on moon is 1/6 of the weight of that object on the earth, right? For example, here, which means if you take the same object to the moon, its weight will be less, right? Very simply. Example is given. The weight of a man whose mass is 60 kilograms is 600 newtons on the earth, right? So how to find out weight? Earlier we discussed weight equals mass multiplied by the gravitational force. So on the earth, gravity is 10, therefore 60 multiplied by 10, 600 newtons. Okay? The weight of a man whose mass is 60 kilograms is 600 newtons on the earth. And the weight of the same man on the moon will be only 100 newtons. Right? 1/6. Okay? But his mass will remain unchanged at 60 kilograms on the moon. Wherever he is, even on the moon or even on the earth, his mass will be still 60 kilograms. But because of the change of gravitational force, the weight changes. Right, children? Okay, we will move on to the next. So we have one last assignment to do. Collect pictures, photographs, and diagrams of the instances of applying forces in day-to-day life, and make a collection of information on forces. So you can make a small booklet with these type of pictures. Collect pictures. You can even draw small diagrams. Okay, some of you all are very good at drawing, so you can draw diagrams also. Okay. So you can simply paste pictures, photographs and diagrams, and you can, next to that one, you can simply write what type of force this is, whether this is a pull or a push. Okay, so those type of small information you can write. So what type of pictures to be collected? I will show you in a video. Right. So after watching that video, I'm sure it's very clear what type of pictures that you have to collect. Okay, children, so as I told you all, you don't exactly have to collect pictures. You can draw small diagrams as well. This is also to improve your knowledge on different types of forces, right? And how to apply force as well. Right, children? So we have completed the lesson now. So I hope you all got a better understanding on distance and displacement and also on force. Okay, so we will see the summary to see what we have done so far. Right. The total length of an object in motion is the distance. Right. The straight length between the starting and end points of the motion and object is the displacement. And displacement has a definite direction, but distance does not have a definite direction. Right? And then we learned a pull or a push is known as a force, and force has a magnitude and definite direction, just like displacement. And further we learned that these type of quantities with both direction and magnitude are known as vector quantities. And the quantities without a direction, with only the magnitude, are known as scalar quantities, right? The standard unit of measuring force is Newton. Symbol is capital N. Right? An object at rest can be moved by applying a force on it. We learn about the effects of force. And the speed of a moving object can be changed by applying a force. The direction of motion of an object can be changed by applying a force. And rotation or turning effect can be done by applying a force. And finally, we learn that the shape of an object can be changed by applying a force. So the whole lesson is done. In the next chapter, we are going to do the exercise. So as usual, you all have to write the answers to all the questions by yourselves and be prepared to watch the next video so that you will understand better whether your answers are correct or not.
To watch these important lessons, subscribe to DP Education's YouTube channel right now. Click on the bell icon to stay updated on the latest lessons. Sri Lanka's largest free online school, DP Education.